Hi guys, in this video we are going to discuss the educational code forces round 147 that was rated for Dev 2. So we'll be discussing the problem A, that is matching, then sort the subarrays, tear it apart in black cells. So let's get started with the very first problem. So the problem states that we are given a integer template and we have to replace all these question marks with digits itself. Now as soon as we replace a question mark with a digit, a number would get formed, right? Or I can say as soon as I replace all the question mark with with digits, I would be able to get a number. And by replacing different question mark with different digits, I can come across different numbers itself. So we just have to tell them that how many different numbers are possible, right? So how would we do it? So you can look over here that the string's length is actually going up to 5 only. So you could wonder that, okay, you're going to use a brute force approach over here. But the only problem is that the test cases are also going up to 2 into 10 to the power 4. In that case, it might give a TLE. But let's not talk about it. Let's understand the how can we solve the question and what's the observation over here. Although it's a simple question, so I'll not be discussing in much detail. So the problem simply states that you are given a string, right, wherein you have characters, so or digits from 0 to 9, right, and also question marks. Now for all the question marks, you can replace them with digits 0 to 9. But can you always replace them with a digit 0 to 9? That's not always the case. Reason being that they have said that there cannot be any leading zeros, right? So since there cannot be any leading zeros, hence you have to make sure that the very first character itself or the very first digit you are going to put, that should not be a 0, right? If it's a 0, then the answer is not valid, so it should not be a 0. So it can have any value from 1 to 9, right? So if a question mark is present at the 0th location, in that case its value is going to be from 1 to 9. For all the question marks other than this, the values could be anywhere from 0 to 9, right? So these are 9 possibilities in total and these are 10 possibilities in total. So we'll just have to multiply. So yeah, that's it about the question. The only other check that we have to do is that if the character, so let's say at the 0th index, they haven't given us a question mark, but rather they have given us a digit itself. And let's say the digit is 1, 2 up to 9, that's fine. But if the digit they have given is 0, in that case, we know that the leading 0 is already there. And in that case, we'll simply print that the number isn't possible, or we'll print a 0 directly. So let me walk you through the code itself. Code is actually small and easy to understand. So yeah, firstly, we'll count the occurrences of question marks, right? And if the very first character now is 0, in that case, the answer does not exist, or no permutation of numbers or no possibility of number is there. So we'll print a 0. However, now we'll check if the very first character is a question mark itself, then for that particular question mark, I have 9 possibilities. So I'll say, okay, 9 possibilities for this. And for all the remaining question marks, that would be represented by open minus 1, because open was the count of the question marks. For all of those question marks, I'll be having 10 possibilities. So I'll just multiply them. However, if that's not the case, then for all the question marks, I'll say that I have 10 possibilities. So I'll just take power of 10, the number of question marks I was having. Cool. Let's move to the second question, that is sort the subarray. So the problem states that you are given an array, then you select two indices L and R, right? And then for this subarray L and R, you sort it. So this becomes another array A dash. Let's denote it as A dash. Now they have given you the value of A and A dash, right? So for example, this is A, right? Over here, let's say you selected L as 2 and R as 5. So this is the second index, taking one base indexing, and 2, 3, 4, 5, right? So this is R. For this array, you sorted this particular array. So definitely the results you're gonna get is 3, 4, 4, 7, right? So you're gonna say that, okay, this, if I sort this particular subarray in this array, then I'm gonna get this particular array that is below it. Cool. Now what we have to do is that we have to maximize the subarray. By maximizing, I mean maximize the number of elements in the subarray. So I have to expand its length, right? So how would I do it? Now there are multiple ways of doing it basically, but easy way is that I can say, okay, let me just take you over here. Yeah. So if this is my this is my array, right? And this is my array. So this is my array A and this is my array A dash, right? Now I'll say that as soon as there's a difference in the number, so let's say this is A, this is, okay, so A, B, C is already done. Let's say this is P, this is Q, this is R, this is S, this is T, this is U, right? Now corresponding to this, there would be some elements, let's call them P dash, Q dash, R dash, S dash, T dash, and U dash, right? Now if P is equal to P dash, then it's not necessary for them to be a part of that subarray that was sorted. However, if Q is not equal to Q dash, let's say, or for any element A of I, if it's not equal to A of I dash, that basically means this was permuted, right? So its location was changed. Now, when could array get its position changed? That would be only the case if we have actually sorted a particular array. So we can for sure say that, okay, this is going to be a part of the subarray that we sorted. The subarray that we sorted. I hope that makes sense. Now, what can you do after this? So after this, you can say that cool. Up till this point, I understood what I need to do. So by doing this, I'll say that, okay, this was the first point at which difference was occurring, and this, let's say this is the last point at which a difference is occurring. So definitely this particular part needs to be a part of the subarray, right? What more can I do? So if this particular part is a part of the subarray, can I extend its boundaries? Can I take it to the left and can I take it to the right? Yes, I can, but what should be the condition that needs to be satisfied over here? Now the only thing, if I include P into the subarray, so let's try to understand it by a small example. So we already said that, okay, Q, R, S and T is the subarray that we were considering. So when would I be able to append P over here? So when would I be able to do it? I would only be able to do it if P is the minimum element amongst all of these elements, right? Because if I say that, okay, P is going to be a part of this subarray, then we already know that we are going to sort this particular subarray, right? So as soon as we sorted, the location of P would get jumbled if there's any element that is smaller than P in it, right? Because that element would replace P and P would be shifted by one location at least. So only if P actually is the smallest element of this entire array, right? Only then I can say that, okay, P can be considered a part of the subarray. And I can then extend the boundary to the other element. Let's say there was an element C over here. I can then say that, okay, C is going to be a part if C now is the smallest element amongst all the elements of this subarray, the same logic being applicable. Now, what about the right boundaries? Now I also want to extend my right boundaries. For that, I can say that, okay, like element, let's say Z, can be a part of this subarray if and only if Z is greater than or equal to whatever maximum element they have, right? So if that's the case, then it's good enough, because what would happen is if Z is less than any of the other elements, right? Then when we'll sort it, then Z would get replaced, or you can say Z would be shifted by one location at least, and the other element, let's say this element S was greater than Z, then in that case S would have been placed at the end. So S would have come over here and Z would have shifted to its place. So that is something we had to do. And I think code would make more sense over here. Code is pretty simple for this. Okay, yeah. So this is what we are going to do. So firstly, I'm going to set my first and last, right? That is the minimum, or you can say the locations at which the changes started to happen. So I'm just checking the places at which my A and A dash, or over here I've taken A and B, at which A and B are not equal, right? So I'll set my first and last pointer. So first is definitely going to be the leftmost. So that's why I've taken min, and last is going to be the rightmost. That's why I've taken max. Or I could have like done it in a different way, but anyway, this actually works. After that, I'll say what is the maximum value I'm having for this particular subarray and the minimum value I'm having for the subarray. Now you could have taken a maximum element STL function or a minimum element STL function. I've just ran across the loop so as to calculate the maximum and the minimum values, right? After that, I'll try to extend my left boundary. For that, I'll say I want to do this operation till the time my first minus one. So the element that is just left to my left boundary, till that time that particular index is greater than or equal to 0, so that I don't try to access negative elements or negative indices. I will keep doing this. This is redundant. You didn't have to do this because anyway the elements would be equal. After that, I'm going to say that this particular element at the location first minus 1 should be less than or equal to whatever minimum element I have currently in the subarray, right? Till the time this thing is holding, I can keep decrementing my left boundary, or I can keep shifting my left boundary. Also, I'll have to update the minimum at each level. So that's what I'm doing. And similarly for right, so I'm not going to explain this because these are identical operations. At the end, you just have to print first and last, or the left boundary and the right boundary. Just add 1 to them because they explicitly said to give the answer in 1 base indexing. So that's it for the problem B. Okay, I mistakenly closed the browser. Give me a second. Okay, let's discuss the problem C now. So the problem C states that you are given a string S consisting of lowercase Latin letters, right? In one operation, you can select several positions in it such that no two selected positions are adjacent to one another. Then you remove the characters of the letters on the selected positions from the string, right? Now, I don't know why they have given it as C and that the question that we just discussed as B. I really feel that this particular question is a bit easier than that one. I'll just explain this question too. And then what they're asking is that since we cannot, remove adjacent characters. So if I'm removing the character at the location I cannot remove the character at the location I-1 or I+1 as well, right? So we'll keep performing operations in this manner. At the end, what we want is, okay, give me a second. Yeah. At the end, what we actually want is that that all the characters actually become same, right? So let me just give you a small example for this. For example, this is the string that we have, right? So I'll say that, okay, in one operation, I'm going to remove B. As soon as I remove B, I'm going to get the string AA, all of whose characters are equal, right? Or same. So in one operation, I can do this. Now let's say I had a string AB. In that case, also you consider I'm going to remove this B and this B as well, right? And I'm going to get the string AA. Because in a single operation, you can remove many characters. The only constraint is that they should not be adjacent. So these characters were not adjacent. I was able to remove it. What if I'm having a string ABBA? Now in this case, I can actually remove A and A, right? So let's take a different example now. What if we had ABB, AA and BB? Now what would we do in this case? So we'll say that, okay, we can in one operation we can remove one B, right? We cannot do remove both the B simultaneously because they are adjacent, right? So I'll remove one B, and this would be my string after one operation. That's fine. Okay, yeah, that's fine. And in the other operation, I'll then remove the other A. So as soon as I remove that, sorry, not the A but the other B. I'll remove this B. As soon as I do that, then I'll get the string AA itself, which is actually valid. So it took me 2 operations to do it. But what is the generic formula for it? So I can say that, okay, there are only 26 characters in the English alphabet. So I can try for all the characters. So I can say that, okay, I'm going to try for all the characters. Now what do I mean by try for all the characters? Now at the end, definitely only occurrences of a single character would remain, right? So I would just say that I want that only that character remains in the entire string. So I could check for A, then for B, then for C, so on to so forth till Z, right? Now, if I'm saying that only A remains, that means all the characters that are not A should be removed. So what would happen in that case is, let's say A, and this is the other occurrence of A. Now there could be different or similar characters over here that are not A, right? Now I need to remove all of these characters. Then maybe there are some more occurrences of some other characters than A and so on and so forth. Now I'm not even interested in what these characters are because irrespective of their value, I have to remove them, right? The only thing I'm interested in is what is their length. What is the length of this particular pocket? Let's call it pocket, right? This is one pocket, this is the other pocket, so on and so forth. Now the reason I'm interested in the length of this pocket is because for this entire string, I just want which pocket has the maximum length. Now let's say this pocket, this one, right? The very first pocket has the maximum length, and let's say its length was 8, right? So basically we had 8 characters, right? 3, 4, 5, 6, 7, 8, right? What can I do with this? I'll say I can remove the non-adjacent elements. So in a single operation, I can remove this, right? All of these characters can be removed. The string I'll now be getting would be X, 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 X. That is actually half, right? And then I can remove this elements. Then I'll be getting X and X. And then I can remove one another and then one another. I hope that makes sense, right? Now what I'm trying to tell you by this way is that every time you'll be able to reduce your string by half, right? Or you'll be able to reduce your pocket by half, right? So it will take so you just need to do that, because if I'm saying that this is the maximum pocket having a length 8, then that means the other pockets have a length 7. So if I can reduce this particular pocket in 8 operations, then definitely all the other pockets could also be also be reduced to 0 in 8 operations, or sorry, in I operations, right? Let's say this pocket of length 8 takes I operations, then I can remove all the other pockets in I operations as well, right? So this is exactly what we needed to do. So we just had to calculate the length of the longest pocket, right, for each of the characters, considering that all of these characters, or each of this character is the character that remains till the end, right? We had to calculate the value of the pocket, and then we have to say that, okay, I'm gonna calculate. You can either have calculated the log value, so as to get how many divisions by 2 or halvings you require. So you could have either calculate log base 2, or you could have actually run a while loop wherein you just divide it by 2 in each loop, right? I'll just show you the logic for this. Let me open the code. Yep. Okay. So yeah. So what I'm doing is for all of these characters from A to Z, I'm gonna initialize a pocket. So pocket basically means the maximum pocket over here, right? Then I'm gonna start a loop. In the loop, I'm gonna increment my current only if the current element is not C, right? If the current element is C, then that means a break of a pocket, because let's say you were saying that, okay, A is going to be the last character that you want in the string, and if you're getting the current character as A, that means you cannot have a pocket that is spanning across this, right? I hope that makes basic sense. After that, once I have the size of the pockets, I just need the number of steps, right? So I'll keep dividing by 2 till the time my pocket is greater than 0, right? And I'll note down the steps, and I'll say that since I want to minimize my result, or I want to minimize my steps, so I'll say that result is equal to minimum of results or the current steps I just got, and at the very end I'll print result. Cool, I hope this makes sense. And with this, let's move to the last question, that is black cells. So the problem states that you are given a really long strip of 10 to power 18 white cells numbered from left to right as 0, 1, 2 and so on and so forth, right? Now you are having a special pointer which is initially at the cell 0. So what you can do with this is that there are 3 operations that you can perform. Now either you can move 1 point to the right. For example, if you are at any index x, then you can move to x plus 1, or you can hold down the shift button. That also takes a single operation, or you can release the shift button. Now as soon as you release the shift button, what actually happens is that all the cells that were between the time when you press the shift button and the time when you release the shift button, all of them would be colored black. However, the condition is that you cannot go and color all the cells black, right? So the range at which you can color these cells black is given to you in the form of L, R segments, right? So how would we approach this question? So okay, so let's finish the problem statement first. So then they want to know what is the minimum number of moves that you need to make in order to color at least K cells black. Okay, that's fine. We understood what they actually want from us, but okay, so in a single operation, we can shift to the right. We can either release the lever or the button, or we can either press the button, right? So we cannot release the button before pressing it, and we cannot release the button twice. So that's obvious, I guess. And we cannot also like push the button twice simultaneously or consecutively. So with that, we have to print the minimum number of operations that would be required. And it's a greedy question, just a small observation. So let's say this is the strip that they were talking about, and there would be some segments that would be given to us. Let's say this was one segment, this was other segment, this was other segment, so on and so forth, right? Now it's like the cells would be there in this particular segment as well, or in the segment that is present between the segment A and B. However, since this is not the segment that we can color, so this is of no use to us, right? So what can we do? Now, one important factor is that would it always be beneficial for us if we are given with a segment that has a cell in it, right, which we can color black? Would it always be beneficial for us to color it black? The answer is no. But why is it no? Now, let's say you had a segment wherein there was only one cell that you can color black. So in order to color this particular particular cell black, what you'll have to do is you'll have to perform one operation. So as to like come over here and press the button, right? Press button. Then you'll traverse across it. So that's one step more. And then you'll say I'll release the button, right? Release button. So how many operations does this take? This takes actually 3 operations. Could you have improved this logic? Yes, you could have. So what you could have rather said is that, okay, I'm not going to press this. So that basically means you still did one operation, right? You still did one operation because anyway, you didn't press the button or release the button. You still moved one step ahead, right? And when you get many consecutive zeros or many consecutive cells that you can color, so you can say that, okay, I pressed the button over here. Now I'm having all zeros. So in order to accommodate one more zero over here, or in order to color one more still black over here, I'll just have to add one additional operation, right? So if I use one additional operation over here, that basically means one operation I already did wherein I skipped the previous one. So this, let's say this was the previous one, right? So when I skipped this, I actually performed one operation, right? And one operation I'm performing now, right? So as to accommodate a new zero, okay, this is not a 1 but a 0. Yeah, in order to accommodate a new 0, I'm actually performing one more operation. So the number of operation I had to perform to accommodate that extra single value is actually 2 itself, right? However, if I would have considered this particular scenario, then I would have landed up with 3 values. Okay, cool. So would this happen only in case of 1 or would it happen in case of 2 as well? Let's just see. So let's say you have 2 zeros, right? Or 2 cells in a particular segment. You're standing over here. You move right, you reach over here, you reach over here, right? After that, you say that, okay, I'm over here now. But what if I skip it? So let's firstly understand what would happen if you consider it. So if you consider it, then anyway, the number of steps it's going to take you is 2 plus 2 because there are 2 right moves. And then once you're going to release the button and then firstly you're going to press the button and then only release the button. So total of 4 steps are required. Now let's consider the same case that you got a very long strip and over there you could have added it, right? So let's say you wanted to consider 2 extra cells. Then you could have done it. So 2 extra steps would be required over here. Anyway, you wasted 2 steps over here, right? So the number of additional steps you took is 2 plus 2, that is equal to 4. That is exactly equal to this, right? So either way you could have used this or you could have used the next big block. The answer would still have been 0, right? Or still have would be same. So yeah, from this we understand that the only beneficial scenario where we can say that it might make sense for us to skip a particular zero or skip a particular interval is if and only if that particular interval contains a single cell. But we also have to be cautious about it because it could be the scenario that maybe picking this particular interval up would have been beneficial. Now, you might say that when would that case occur? So let's say we had some zeros, right? And you skipped a 0 over here saying that, okay, I'm going to include the next zeros. So let's say this value was 10. This is 11, 12. These are empty boxes that were not populated. This is 13, 14, 15, 16. And then some empty boxes again, right? 17, 18, so on and so forth. And then some zeros, right? So the problem is now if you say that, okay, I'm going to skip it. Cool enough. You can skip it. Let's say our M or the number of boxes that we want to color was 6 or was 4, right? Now you'll reach till the end of, okay, not 4, but let's say 5. That would make sense actually. So you'll reach till here. You'll say that, okay, I have 4 boxes. So I'll color the 4 boxes. That's fine. But I'm still left with 1 box, right? It would have definitely made sense for you now to actually consider this. But would we go back and then consider this? No, definitely we can't do that because then the complexity is going to increase, right? So what can we do in this case? In this case, we can keep a counter of the number of such cells wherein there was only a single zero present, right? Or a single cell present in the interval. We can keep a count of them and when and if required. So if it's required that we can get our answer done with by including the number of such cells, we'll utilize them then and there. Maybe I'll show you the code. It would become more comprehensible or more understandable. Cool. So this is the code. Firstly, I'm taking the input. So I'll not be discussing that. That is trivial, right? Then I have to sort it. because I want to move from left to right. Right. I think they had already sorted it, but it won't hurt actually. Order of n log and really won't hurt over here. Right. Now this is rem, which actually means that how many single cells were there which I traversed. I didn't add it to the answer. This is the number of operations. So you must notice that over here the operation of number of operations only mean the number of times you pressed and released the button, right? And then you have a result that is set to long max. Okay, button. Okay, never mind. Let's not write that. What would you do now? So you'll say that I'll traverse across all of these segments, right? Then you'll say that if the current segment, if it's more than enough to complete my answer, in that case, I'll use that. That obviously makes sense, right? If the current segment can complete your answer, why would you even move further? But what would be your answer in that case? Cool. So you're gonna say that, okay, I don't want the entire segment. Maybe I want it. Maybe don't even want it. Let's say your entire segment has maybe like 10 cells, right? And you only require 8 cells. In that case, it won't make sense to go till the 10 cell. You can complete your algo by the 8 cell itself. So you'll say that I'll go to L plus M minus 1. So L is a left boundary and you need M cells, right? So M minus 1 would represent M cells because L is also being considered. That's why I do minus 1 over here. Then you say that, okay, I'm going to perform 2 operations as well. So as to press the lever, press the button and release the button. That's cool enough. Plus 2 for that. And plus OP, because OP actually means the number of operations that you have already utilized, right? So yeah, that's what you're going to do. And then you're going to break it because you already got your answer. Else if it could be the scenario that individually it's not enough so as to get you all the black cells. But when I consider this particular number, that is the number of white cells I'm having currently, along with the number of single cells I already left before me or to my left, right? And if that is greater than or equal to M, in that case, I can collectively use them so as to form my answer. But wait, what would be the answer in that case? Now, it's obvious that for the current cell, right, let's say it has 10 cells, right? Just giving you an example, right? And maybe the number of cells in totality we require is maybe like 15, right? And the number of remaining cells or the number of single cells we already left to our left are maybe like 10, right? In that case, let's make a different number. Let's make it 12, right? In that case, it would only make sense for me to consider all the 10 cells from this subsegment, right? I'll consider 10 cells from this segment. How many more cells do I need? I require 15 minus 10 more cells, right? For those, I'll consider these 12 cells. Cool. So that's what I'm going to do. So I'm going to say, I'm going to utilize all your cells. So you're going up till R. I'm going to utilize till R, right? So R plus 2 basically means holding down and releasing the lever or the button, plus OP. OP is basically the number of operations you have already consumed, plus M minus the number of cells you consumed from this, because this would mean the remaining cells, right? Or how many cells you require more, right? And you're going to take these cells from the single cells that you have already traversed, right? So you'll say that, okay, for all of these cells, I'll need 2 extra operations, one to lock it or to press the button and then to release the button, right? And you'll store this value in minimum or in res, right? Whatever the minimum of res comma this particular value is, you'll store that. After that, you'll say that, okay, if the current, so this processing is done, but now I want to know that if the current cell was having a single cell itself, in that case, I want to increase the number of single cells I've observed. So rem plus plus. Else you'll say that, okay, I'm going to consider the particular block. If you're considering the particular block, you'll have to say that the number of operations would increase by 2 because you had to press the cell and to release the cell. Also, the number of white cells that you have traversed or the number of cells you have made black, right, are gonna decrease by the number of cells that were there in this particular segment. So R minus L plus 1. After that, you just check. So your dummy value initially that we had provided was long max. So if it's still same, then in that case, you couldn't complete your algo and the answer does not exist. In that case, print a minus 1. If that's not the case, then you can print whatever result you are having, right? So yeah, that's it for this particular problem. I hope you understood it. If you still have any doubts, let me know in the comment section below. Cool guys, thanks a lot. Bye bye.